Hello everyone, this is Syed Shadi and I am going to talk about electrical resistivity tomography from zero to hero. This is session number 2 and I'm going to talk about resistivity surveying. In this video I'm going to describe what is the procedure to do a resistivity survey, how we can calculate the parallel resistivity values, what is the concept of array, and what are the different types of electrical resistivity surveys. Before we get started, it's important to note that whenever we're going to do a geophysical survey, we must be aware that we have the contrast. So in electrical resistivity survey, we should be aware that whether we have good and enough resistivity contrasts of our targets with respect to the background, and whether there is an acceptable signal to noise ratio, because these are the prerequisites for electrical resistivity surveying, and so do for ERT. The figure below shows several examples about different anomalies that we should expect in different situations for cavity, whether it is filled or not, and whether it is below the water table or upper the water, below and upper the water level. So, for example, in the figure at the center, we have a dry rock and the hole is being filled by water, so we might expect the decrease in apparent resistivity in this case. Please look at the other examples with the notes to get more details about the concept. Okay, electrical resistivity surveying. So, as I have discussed, it is very simple. We measure electrical resistivity surveying by measuring the voltage difference between the receivers and the current intensity that is injected to the ground. So the current electrodes or the transmitter pairs are usually denoted as A and B, or C1 and C2, while potential electrodes are usually denoted as M and N, or P1 and P2. So we got 4 electrodes, 2 receivers and 2 transmitters, and we send the current and measure back the signal. It is very easy to understand, and we got the current lines. The current lines are drawn as red lines, and the equipotential lines, the lines that have the same electric potentials, are drawn as blue. This as the schematic showing, and you see that the electrode is in fact a kind of stainless steel or bronze that is injected into the ground by hammer or something like that. And then to have a better conductance and better connection to the ground, we usually use salt water or bentonite mixture to ensure high contact of the electrode to the ground. And this is the cable which connects our electrodes to the measurement systems, and then we will have the capability to measure the difference in potential, for example, in between this electrode and the other. So it's very simple, one of the most simple geophysical methods to do. So electrical resistivity survey, the main question is that how we calculate resistivity by having resistance values. Let's take a look at the previous session, and this is the equation that I have discussed in the previous session. And if you remember, we talked about resistivity and resistance, and we emphasized that these are different. In electrical resistivity surveys, as I discussed, we measure resistance, the voltage divided by the current intensity injected into the ground. So we need to have the geometric factor to correct for geometrical effects in the measurement to have the resistivity to be independent of the geometry of the objects. So we will be able to calculate the resistivity value by this. So rho A, I will discuss why it is A. This is in fact apparent resistivity, not the true resistivity. I will go to describe it in a few minutes. This is the delta phi over I. This is the resistance value. The phi is the potential, the electrical potential, and delta phi is in fact the differences of potential, or the delta V, or the voltage difference between the receiver electrodes. So this is the intensity of the inserted current into the ground, and this K is called as geometric factor, which corrects for the effects of geometry and our measurements, and it is related to the location of the electrodes and the geometry of the system that we have used for our measurement. So it uses this equation, and this equation is comprised of just distances, so the geometrical parameters, and that's why we call it geometric factor. This is the distance between C1 and P1 electrodes, the distance between C2 and P1 electrodes, C1 and P2, and C2 and P2. So whenever we have the location of the four electrodes, we will be able to easily calculate K, and then we put the K into this equation. We have the delta phi over I, or the resistance value. Then we will have the capability to calculate the apparent resistivity. And what do we mean by apparent resistivity? Apparent resistivity is in fact not the true resistivity of the materials in the subsurface, and in fact it gives us the resistivity of a homogeneous ground that would be measured with the same electrodes with the same positions that we have used. So at this point, this formula will give us apparent resistivity, and it is different from the true resistivity of the materials of the subsurface. And in fact, there is a relationship between apparent resistivity and true resistivity of subsurface materials, but it is complex, and we solve this relationship by something called inverse modeling, the inversion. And the inversion will provide us and will take us from apparent resistivity values to the true resistivity values of the subsurface. We will discuss in detail in next sessions about apparent resistivity and the inversion process, and so many other concepts involved in this process. Now I would like to describe a concept which is called array. You might have heard about it. Arrays, in fact, is the specific arrangement of a transmitter and receiver electrodes. So it is also called the electrodes configuration. Let's take a look at this. These are several, well-known arrays. This is, for example, Venera alpha. It is also called Vener. So it gives us the way that the electrodes are placed together to measure an electrical resistivity survey. So in this case, for example, the Venera alpha, when we say we're using Venera alpha array, it means that we use current electrodes, then we have potential electrodes, and then the second current electrode. Means that the potential electrodes are located between current electrodes in a line, and all of the electrodes are A meters apart. They are spaced at equal distances with respect to each other. So when we say Venera alpha, everyone will understand this. And whenever we say, for example, we have Venera alpha, measurement with A equals 3, everyone knows that the C1 is, for example, is in 0, P1 is in 3 meters, P2 is in 6 meters, and C2 is in 9 meters. The Venera beta is different. It is C1, C2, then P potential electrodes. The potential electrodes and current electrodes are placed together, but they are all at same distances with respect to each other. And Venera gamma, in Venera gamma we have current potential, current potential. totally in electrical resistivity surveys, we have three types of arrays. Alpha array types are those arrays that the current electrodes are on the outside of the system and potential electrodes are inside. Beta electrodes are in the systems that potential and current electrodes are together. And our gamma array types are the electrode arrays that potential and current electrodes are located in between each other. For example, C1, P1, C2, P2. We have a dipole-dipole array, which is very familiar for most of you. And in this array uses C1, C2. This is an alpha array type, in fact, so C1, C2, P1, P2. But the current electrode pair with respect to potential electrode pair are located, different from what is in the winner. So it is n times of alpha and n times of R. So, for example, if A equals 1 and we say that for example, n equals 3, everyone will understand that what we are just talking about. So the characteristics of this dipole array will be parameters A and n, but Wenner is just one parameter. We also get Wenner-Schelumberger array. It is on an alpha array type. Sorry, I made a mistake. I think I told that the dipole-dipole array is an alpha array type. Dipole-dipole is a beta array type. And Wenner-Schelumberger is an alpha array type in which the P1 and P2 are close together, and the current electrodes are at the end of the line. We got the pole-dipole array. The pole-dipole, one of the current electrodes are located at infinity. What we mean by infinity is that one of the current electrodes is located too far from all of the electrodes and far from the line to have any effect on the measurements. In fact, not any effect, but its effect will be minimal. And pole-pole array will be has this configuration, and we have two electrodes at infinity, one of the potential electrodes together with one of the current electrodes. And note that C1 and P2 are far away from each other. And this is the gradient array, which is a very familiar and very well-known array. In this array, it is an alpha array type, but instead of taking one specific measurements, any potential pair within the C1 and C2 can be measured. For example, P1 and P2, P1 and P3, P1 and P4, P2 and P4, till the end of the possible measurements. So we've talked a lot about arrays, different arrays. So these arrays have different characteristics. Each array has its own characteristics. They have advantages and disadvantages, and in this point I want to emphasize that there is no best array. We don't have it. The best array doesn't exist for our conditions. We have optimum choice for a survey. For example, each array can be an optimal choice for a survey according to the site conditions, target specifications. For example, if we have a target at very high depths, just several type of arrays can provide us reasonable responses and can be useful even, rather than providing a very great result. So when we're talking about deep targets with respect to shallow targets, when we're talking about smaller objects with respect to big targets, they might not be the same, and they are not the same, and the array choice would be different in these different cases. And I won't go through much more detail about the arrays because it requires a term which is a sensitivity function, and I will discuss it in the next session. So when we have discussed sensitivity function, I will go through the characteristics of array in more details. So these are the arrays that I have just discussed and I have showed. to you. Let's go ahead, and now I'm going to talk about different resistivity survey types. We have 1D, 2D, 4D, and 3D surveys. In fact, the main characterization is regarding the in fact, the main discretization between this type of surveys is regarded to the assumption that we make rather than the number of the dimensions. For example, in 1D survey or 1D model, we assume that the resistivity is not changing in two directions and is fixed in two directions and is just variable in one direction. So in this case, we assume that the resistivity is only changing with depths. We can have several horizontal layers with different resistivities, but they cannot be, for example, dipping layers or these kind of things. This is like that. When we talk about 2D models, we assume that one of the directions is extended toward infinity. And in this case, that we have shown, the direction towards the screen is going to be extended to the infinity. And in the 3D, there is no assumption such as this, and it has effect. And in the end of this video series, if there was some time to talk about it, I will talk about the effects of, for example, the effects of 3D effects in 2D models. So let's take this point that time-lapse measurements, time as a dimension, can also be taken into account. So sometimes 2D ERT surveys that are, time-lapse 2D ERT surveys, making 2D ERT measurements at different times can be regarded and can be called as 3D survey. And definitely the time-lapse 3D ERT is sometimes called as 4D surveys. So take this for granted. So first I will go through the 1D survey and the terms profiling and sounding. These terms might not be directly related to ERT, but it is good to know. And you're just working in the geophysical domain and you're working with ERT, it is good to know about that. So in profiling, we examine variations in horizontal directions, and it is well known in geophysics. So in profiling, for example, if we have a ground that is like this, has a rho 1 and an anomalous area with high resistivities with rho 2, and we use, for example, some kind of arrangement like this, looks like a 1 or alpha array. So we measure this electrode C1, P1, P2, C2, the red configuration, and it gives us the response from here, for example. Take this for granted. I will discuss much more about the location of the data points and the true resistivity, apparent resistivity. All of them will be discussed. So if we consider the measurement point of this, red is going to be this point, and then we're going to calculate the apparent resistivity based on the geometric factor and the resistance that is measured. So we're going to have an apparent resistivity like this. And then the whole system moves forward in the direction of the profile. Then we will have a blue reading. The blue reading will provide us information from here. For example, the apparent resistivity of the blue will be like this. Then again, we're going to move forward, and the electrodes are going to be moved again, and we have these configuration in this point. So between P1 and P2, the green measurement will be this, and it is be affected much more by the rho 2. So we'll have an increase in apparent resistivity calculated, and then when we have crossed it, it again goes back to a value which is dominantly controlled by rho 1. So this is the profiling concept. It provides information in one horizontal direction, and it assumes that the variation is just in horizontal direction and in the direction of the profile. So it is this simple, yeah. In the sounding, it is different. We assume that the variations are not in horizontal directions but in vertical directions towards depths. So if we have a row 1 layer and beneath that we have a row 2 layer which has a higher resistivity value, we may use some kind of Venner-Schellenberger array. We will measure the potential difference between P1 and P2 when the transmitter is sending the current through the red C1 and C2. It's going to be providing information about this point. Then the electrodes are moved forward, the current electrodes, to let the current go deeper into the ground and provide information about deeper depths. But the potential electrodes are fixed. So in this case, for example, the N of the Venner-Schellenberger array will be 2. In this case, again, we calculate the apparent resistivity by having the resistance with geometric factor, which will be different from the first measurement. Then we are going to plot the blue, and then we'll go extend the current electrodes to C1 and C2 of green, then light blue, and then we'll have a curve like this. This is the apparent resistivity, and this is the pseudo depths. And why we are calling the pseudo depths, we're going to have a lot of talk about that. So on the whole, it makes us to measure the differences in vertical direction. So sounding provides information about towards depths, and assuming that we have no variations in x and y directions, just towards depths. Okay, what about 2D? The 2D, in fact, now we can call it tomography, because the 1D is not tomography, but the 2D and 3D is tomography, because we are having several values and the variations more than one direction, and then we can interpolate, and then we have to say that it is a tomography. So in the 2D survey, we consider and we measure electrical resistivity and in two directions. In one direction towards the spread of electrodes, for example, this will be the x direction, and then the other will be towards depths. So we'll get some image like this. We don't have image about the cross line, perpendicular to the line, but along the line direction and towards depths we'll have an image. So it is called 2D electrical resistivity tomography. Sometimes it is called electrical resistivity imaging, but it is not much more common. The ERT is much more common. And the 2D ERT survey, this is the pseudo section of a dipole-dipole array, and what we mean that, for example, we measure these data points and then we interpolate those data points. I'm going to talk about that more in next sessions. I don't go through the details. You're going to there's a much difference between pseudo section and the true resistivity values. In fact, the pseudo section is the section that is provided by interpolating the apparent resistivity values, the values that are not the true resistivity values of the subsurface. I'm going to talk about it more in next sessions. And this is the several examples of the real true resistivity values after inverse modeling or inversion, and in the end of this series you will be able to create this. So in this case we will have the tomography, the variations of electrical resistivity in wide areas towards the profile, in the profile extension direction to, and also towards depths. This is the interpolated model, or the smooth model, the interpolated model, and this is the blocky model. And this is several profiles, several 2D profiles together in Some of the time it is called 2.5D model. And let's take a look at this. This example is from Dentist and March 2014, the great book which I advise you to read it if you're going to really learn about electrical resistivity and IP. Especially I advise you to go through the basics of resistivity and IP and the causes and the reasons of resistivity and IP variations. But the inversion and the inverse modeling part is not that good. If you're going to cover that, you have to put aside 2 course notes or the tutorials of Dr. Luke, geotomosoft.com. That is, these 2 together can be very effective to learn. So in this case, for example, this is the apparent resistivity values, and this is the true resistivity after inversion. And I would like to note that the variations and the difference between apparent resistivity and true resistivity, for example, take a look at this point and this point. So that's why and how we mean that the apparent resistivity is not the true resistivity of the subsurface. So and it is the dipole-dipole array. It is the ERT and IP tomography survey of the the phase angle, and it is the frequency domain IP of the Olympic Dam giant IOCG deposit in Australia. If you're a geologist or working in the mineral exploration, you have definitely heard about this amazing deposit. And they have used a fascinating survey, and if you look at the depths, it's up to a depth of 1 kilometer. It is amazing. This is another example from a paper that was exploring for sinkholes or caustic features, and they have delineated low resistivity anomalies in high resistive limey units. I think it was in Korea. I don't remember the study area or the name of the writers. This is another example. I think it was one of the Dr. Dalin's papers. And this is the application of ERT for waste pond detection. Now, this slide is about 3D and 4D ERT surveys, and it is an embankment which was mapped by 3D electrical resistivity tomography. This is another example, and in fact it tells us the high values of resistivity in 3 dimensions, very accurately mapped, and we can create isosurfaces if for example, high resistivity or low resistivity features are in our interest, is a target of our interest. And this is the plan sections of 3D ERT of performed in Res3D and from the surface to the depths like this. This is another example from Dr. Luke's notes about sludge pond detection in 3D ERT. So it has diverse applications, and it has a lot of different applications. In this session you have you have gained knowledge about the basic concepts about resistivity tomography, how we calculate the apparent resistivity, and what are the different types of electrical resistivity survey. So in the next session I'm going to talk about sensitivity function and depths of investigation. If you have any questions, you can email me at the following address, and if you liked our video, just share with your friends and follow for more.